Welcome back to the Dunbar Motors channel. I'm your host Dubar, and we're going to dive right into a new video that discusses one of the many things I've been working on. Special thanks for this diagram of a turbocharged engine goes to Saber Fallah from his book titled Electric and Hybrid Vehicles, Technologies, Modeling and Control, a Mechatronic Approach. To save time, I won't be discussing how a turbocharger works, but a picture speaks 1,000 words, am I right? Okay. There are two kinds of anti-lag systems that involve sending unburnt fuel with various sources of air into the exhaust manifold, causing an explosion in order to spin the turbo faster. There's also a rocket anti-lag, but all three of these burn extra fuel and produce drastically more emissions than a turbocharged engine would alone. In this video, I'll be discussing a compressed air anti-lag system that uses high pressure compressed air to increase pressure in both the exhaust manifold and intake manifold while reducing emissions. In addition, these increased pressures are accompanied by reduced temperatures in both the exhaust manifold and charge air. In this example of the compressed air anti-lag system, a 12-volt compressor turns on at 70 psi and turns off at 120 psi and draws about 12 amps. When the pressure from the compressor enters the cowls valve entry port, it's then directed into the storage tank. Once the pressure at the entry valve is lower than the tank pressure, the valve will then direct the entire contents of the tank out the exit port of the valve directly into the exhaust manifold. Once the pressure at the exit port and the entry port have stabilized, the valve will automatically close, or when the solenoid is allowed to close, then the system will automatically repressurize, closing the valve instantaneously. A standard compressed air nitrous tank exceeds the pressure demand, so that's what's used in this example. And also in this example, the pressure differential is introduced by a 12-volt solenoid, which directs the pressure from the compressor side into the intake tract. It does this before the intercooler, reducing temperatures so that it's actually increasing pressures at both the intake and the exhaust manifolds, while introducing fresh air to both and reducing emissions and NOx gases. Okay, so to visualize that, you can see here that with the system turned on, the compressor will fill up the tank to 120 psi and then turn itself off. As you can see, the solenoid is closed. Once the solenoid is open, the entire air mass in the storage tank will instantly be sent into the exhaust manifold, spinning the turbocharger just like it was an explosion, except it's fresh air and there's no additional fuel. That'll actually lower those NOx gases. And what you'll also be seeing is all the residual pressure that was on the entry port side in the compressor lines. That's going to go into the intake side. That's going to lower your intake temps as well as supplement the pressure that's in there. Because there's no ignition cutting or fuel being injected into the manifold, you don't need to worry about extra special tuning. Your wastegate and your blow-off valve or circulation system should still work just fine. And I'm thinking ideally your turbo will have lower temperatures while actually having higher pressures. And as far as I'm concerned, that's going to be a big compounding win. So that's sort of the discussion there. If you're curious, feel free to at me in the comments, or if you think I'm wrong, let me know. I'd love to know if or if not, whether it'll work. So if you feel like touching base, let's touch base. If you want to try it, let's talk. Thanks. Oh, and be sure to like and subscribe because I'm going to be discussing more of the actual components while I test these things. Right now, I'm just in the theory stage, and there's a ton more for me to do. We'll see you soon.